In this video we're going to look at the general architecture that we're going to use for our adder and subtractor. Now the architecture we're going to be working on through the rest of the course is this one on the right hand side, and this is called a dual path architecture, and you can see why, because the path is split into two. There's a near path and a far path. Now what we'll do is we'll compare the simple architecture that we have here on the left, and we'll compare it to this dual path architecture through this video. Now I'm going to be jumping back and forward through the subtraction algorithm and the addition algorithm, and we're going to pick out the points in these algorithms that are the same, because we want to reduce any redundancy in this simple algorithm on the left. Now by reducing redundancy, what we do is we ensure that the design that we end up with has got a better latency. So basically really all we're saying is we want to make sure that the architecture we choose is fast. So the architecture on the right hand side, the dual path architecture, is faster than the architecture we have on the left. So let's talk through the architecture we have on the left hand side, and we'll equate each of the boxes to each of the processes we go through here for the subtraction algorithm and the addition algorithm. So you can see, first of all, if we look at the subtraction algorithm, we did have the option here where we had a plus and minus button. So this would be given by, in effect, the symbol here. So if it was x minus the value of y, in order to do that minus, we add on the negation of y. So that's the same as x plus minus y. So if that button was pressed, then we know that we're going to have to invert the y to become minus y. Again, if the button is pressed and it's a minus y, the minus y will become a plus y. So that's just the negation of the y. Now that happens whether we're doing the addition or the subtraction. So that's going to be our first box. Our first box here is the add and subtract button, and if it's pressed, then we're going to do the negation of the y value. Now the next thing we're going to do is compare the exponent, and you can see that compare the exponent, we want to ensure that ex is greater than or equal to ey, and we do that whether we're doing the addition or the subtraction. So the same line appears here. So it means that the second box down here is compare the exponent, and you can see that that happens in both architectures. Now this is where it starts to differ. You can see again, if we get into the addition algorithm, before we can add them, remember we had to make the smallest exponent equal the largest exponent. So in order to do that, we also have to ensure that the mantissa went down by that respective amount as well. So this was the change in the mantissa value. So the mantissa value changes by a factor of beta to the difference between the two exponents. So this happens whether we are doing the addition or the subtraction, and you can see it occurring here within the subtraction. So if we head up, you can see that we've got our alignment shift. So that's us shifting the mantissa so it's in the right position. Now if we continue on with the add and subtracting, you see here that we're also going to either add the mantissas together, so that's the addition here, or we're going to subtract them. So we've got, again, up in here, we've got our add and subtract the mantissa. Now a little note here, which is a little bit different. You can see the next one says conversion. Now we mentioned before that if we were going to do this subtraction, then we're going to use 2's complement. But there was a possibility that whenever we subtracted the number, we ended up with a negative 2's complement. So in that case, we had two options. We could leave it in 2's complement, and we could change it back into just a sign and magnitude by inverting the answer and adding 1. Now the other option, and this is the option that I decided to go for, was we could make a comparison with the mantisas for both the values, and we could ensure that we only ever took the smallest mantissa away from the largest mantissa, and this would ensure that we always got a positive result, which a positive 2's complement number would be exactly the same as a sign and magnitude number. So in effect, these two options that we came up with, these two options can really be classified in that one box, which is the conversion. So it's just to make sure that the answer actually comes out in a meaningful sign and magnitude number. Now the next thing that we would do if we went into the subtraction here is the a normalization phase. Okay, so now in fact we've went through the addition or subtraction here, and now we're heading down to the normalization. So for subtraction, we can see that if the value of MR is less than 1, we get the cancellation, and if we get the cancellation, it means that we're going to have to change the exponent value. So the exponent value gets changed by this value of lambda, which is the leading zero count, and also the value for the mantissa increases by that same factor of the leading zero count. So in effect, we're going to have to count the leading zeros, we're going to have to do the shift, and we're going to have to pass on the value lambda to the exponent. So all of that really is taken care of in this part here, which is leading zero count and shift. Now it might be a case that there aren't any leading zeros and we don't do that shift. Okay, so if leading zero count is 0, then it means that we didn't have any cancellation. If we didn't have any cancellation, then we would just go through the normalization phase. Okay, so the normalization phase here for the subtraction is just this one here. So there wouldn't be any ripple and there would be no change in the mantissa, so there wouldn't be really any normalization. So either for subtraction, either we have the cancellation or we have just the no normalization. Now obviously we'd have to look for the addition as well, but in the addition, again, it's simpler. In the addition there's no cancellation, and we would either ripple through a value of 1, and up here we'd ripple through a value of 1, and the exponent would change by a factor of 2, or there would be no normalization. So that's really taken care of again in this box here, which is the normalization and shift. Now finally we would do our rounding and we get our final result. We've not talked much about rounding, but we will in a later video. So you can see here then we've got 1, 2, 3, 4, 5, 6, 7, 8 processes that we're having to take care of. Now we can simplify this in such a way that instead of having the 8 processes, we're going to have 1, 2, 3, 4, 5, 6 processes only, and the 6th process is actually a very simple mux just to choose between the two. So in effect we could really say we're going from the 8 processes here to the 1, 2, 3, 4, 5 processes here. So we're cutting down 3 of the processes by making this a dual path architecture. So let's talk over this dual path architecture. We're going to have the add subtract button, the same as this one. We're going to have the exponent compare, which again is just the same. But then we're going to split into this near and far path. So let's first of all look back and we'll see the subtraction. So in this subtraction, we're going to have two options here that we're going to work through. We're going to have option 2 and option 3. So these are two options for the subtraction. Now we're also going to have two options for the addition, and that is the option 1 and option 2. So in effect, we've got four things that we need to do. So in the dual path architecture, we have one dedicated path for this option here, which is the cancellation. So if there is a subtraction and the value for this MR is less than 1, then we call that cancellation, and we have to do the leading zero count when we have to adjust the exponent value accordingly and also the mantissa value. So this part of the architecture here only is used for cancellation. So in effect, this gets used for this is 1/4 of the possible values. So if we were to get into the subtraction again, then this one's taken care of by that path. Now this one here goes through the other path, which is the far path. And then if you go to the addition, we've got the options 1 and 2. Both of these go through the far path. So there's only one that goes through the near path, and that is if we get cancellation. So that gives us or tells us exactly what the paths are used for. Now this one here is called the near path because it only operates on the paths which have got an exponent number which is a value of 0 or 1. That is, the exponent for x and the exponent for y are close to one another. They're either the same or a difference of 1. So how does this dual path architecture cut down in the number of processes? Well, if we were to look at the left hand side here, which is the near path, so this is for the subtraction where we get cancellation, then you can see that we're going to cut down on this alignment shifter. Now we're not going to shift it by any more than a factor of 1. So we can add in just a simple 1-bit shift here. So there's not going to be any large alignment shift in this. So in effect this disappears and it gets replaced by a simple 1-bit shift, because this side here is only going to be a difference of 0 or 1. So it means that the exponent only gets shifted by a value of 1. We then go through the normal mantissa add and subtract, and we go through the conversion phase, and we go through the leading zero count, and this then at that point is actually normalized, and we come back out and we make a choice between this path and that path. So that means this process here is 1, 2, 3, 4, 5, and then just a small path selection at the bottom. So we've managed to miss out the normalization shift and also the large alignment shift here. And you'll notice as well that there is no rounding here. Now there is no rounding because whenever we subtract off the two numbers which have got an exponent value of only 0 or 1, then we're going to get an exact result. Now that might not appear obvious to you, but what I'll do is I'll add in a video in the appendix section and I'll go through a little proof of that. So it means we no longer need the rounding in this section as well. So we've saved 3 sections here by splitting into the near and far path. So let's look at the far path. Now we mentioned that if we look at the subtractor here, that this one is the near path. The other one here is going to be taken care by the far path. And you can see in the far path here that we don't have any ripple through, and we've got no change of the mantissa, and we'd have no normalization required here. So this is actually taken care of in the same process as we do for the addition. So the addition here again, there's no ripple required, no change in mantissa, and there's no normalization. And the other option for the addition is a simple normalization by a value of 1. So we ripple 1 through the exponent and we change the mantissa by a factor of 2. So all of these options are taken care of in the far path. And you can see that we go through our initial large alignment. So in effect, that is going to be this alignment here. So we do that for alignment for the subtraction, and we also do the same, the alignment for the addition. So having done this initial alignment, we therefore head on, and we don't need to do the, we can do the adding and subtracting, but we don't need to do the conversion phase. Now there's no conversion phase needed because we know whenever we're doing the subtraction down this path here, the exponent value is going to be a value which is greater than 1. So we know that it had already been swapped over, and we would be subtracting the largest value from the smallest value. So we won't have a negative answer in here for this particular far path, so we don't need to do this conversion. And then we take care of the rounding here, and then we head out through the path selection. So that means again we've only got 3 things we need to do down this path here as well. So you can see that this near and far path architecture is able to cut down some of the processes that you need to do if you were going through this architecture, a simple architecture on the left. But still, we've got to go and build this up, so let's go in the next video and we'll actually physically we'll create an instance of this which we can then use in order to build something in Logisim. Thank you for listening. I'll get you on the next video. Goodbye.